Okay, hello guys, welcome to this video. In this video I'm going to show you how to do this particular exercise. So the exercise is to find the dimensions for a reinforced flexures for a linear guide. Now the height of the total flexure, so including the reinforced part, so here is the flexure with the reinforced part there. The full length has to be 100 millimeters. 100. Now the thickness, the width of the flexure, so this value, that's 30 millimeters. The material that we're using is 210,000 megapascals, so 210,000 megapascals means it's steel, right? Steel. Then we have a relative displacement of 2 millimeters plus and minus in the direction of y. So that means that we are going to put a force over here. Hey, that's nice. There. Yeah, okay. Anyway, we're gonna put a force over here, and the force can be 9 newtons. And if we put 9 newtons on here, we have a displacement of 2 millimeters. That's required. So x1 is 2. And that's not everything, but there's also a load on top. So there's a load on top, and it is 3000 newtons. Now, what they want us to calculate is what the flexure dimensions can be with the reinforcements in order that we don't have buckling at 3000 newtons, but still that is compliant enough that in the 9 newtons it will give us a displacement of 2 millimeters. Alright, so what you will find is that we have two variables that we really don't know. One variable is of course this one. It's the value for P times L, so the value for P is unknown. And P is always a factor, so if L is 100 and P is 0.8, that means the 80% of the flexure needs to have this reinforcement. So the P value is unknown. Also, the thickness, basically, the thickness T, is also unknown of the flexure. So these are the two values that we can play around with. So what we'd like to do is we'll find a formula where we can basically describe P as a function of T, or sometimes it is H or whatever. So P as a function of T, that's what we want. Now first let's see in what kind of ballpark we are. So the first thing I'm going to do is I'm going to calculate how much force do we actually need. Sorry, how thick should this thing be if we have no reinforcement whatsoever. So then we get this formula, which is the stiffness K is 12 EI over L to the third. Alright, now the stiffness K we can find because we knew already we had this system like this, and there was like this, and we have basically two flexures that are being set up like this. Well, something like this. Now this thing had a displacement of 2 millimeters with a Newton, with a force on it of 9 newtons. So that means that the system stiffness is of course 9 over 2, or 4.5 Newton millimeters. There we go. Also what we know is that we've got two flexures working in parallel. So we know that K system, right, is K1 plus K2. Since both of these are the same flexures, at least we're going to design it in such a way that they have the same dimensions, we can just say that they are 2 K1. So basically K for both 1 and 2 is K system over 2. So what we basically get out of this is that the K for one of these flexures is 2.25 newtons millimeters. Alright, so that's just a little bit of a side note. So let's delete all of this. There we go. Just write down 2.25 n millimeters is K. Alright, so that is something we can fill in over here. Well, we know this one, 12e. The I I'm not quite sure of, because I is of course bh to the third over 12. 1/12 bh to the third. And this one we also know. That's fine. So over here that h is the one unknown in the system. So what we of course can do is we write the system so we have I outside of it. So what I always like to do is I say k over 1 is still the same. Then we cross it. It's 12 ei. 1 times that is the same as k times l to the third. And we want to know the I. So we have to divide over 12e. Then we can throw this away. So I is k l to the third over 12e. And if we put that in our calculator, I quickly will do it over here. It's of course 2.25 times 100 to the third over 12 times, and then we've got 210 times 10 to the power of 3, and we get an I of 0.89, well, something 3 millimeters to the fourth. Now we also know that I is b times h to the third over 12, right? So we can also kind of rewrite this in a way that we know, so again, I over 1, so that means 1 times bh to the third is I over 12, yeah, so that means times 12, yeah, over, and then we've got b is h to the third. And we can also, that's the nice thing of this, I can just put this a little bit over here. Say this is the third square root of it. There we go. That gives me h. Now I know I because I've calculated over here. I plug it in into my formula. I know b, which is 30. So we can plug everything in. And let's see what we get then. It is the third square root. Sorry. Third, 0.893 times 12 over 30. Let's see, and that gives me 0.709 or 7.1, so 0.71 millimeters. Now, what did we calculate here now? We calculated that if we want to have a K value of 2.25, that the thickness of my flexure without reinforcements has to be 0.71. Now, this is relevant for a few reasons, because later on we are going to plug in some values, and we know that whatever value, of course, if we are reinforcing this flexure, that means that the thickness has to go down. It can never be more than this value. So what we've calculated here is kind of a boundary condition. If our value is more than 0.71, then even if I have a very little bit of reinforcement, it will already surpass this K value. So, alright, that's one thing. Now, next up, what we can do is we are going to calculate what the buckling forces are. So you can find this in your book. It's in chapter 6. And over here we can see what the buckling formula is. Or no, we can't. Well, I can write it down over here. The critical force, so basically the buckling force, is 4 pi squared times EI over L squared, and then we have 1 minus P squared fully. Now this is the formula for the buckling. Now what we know is that we have this system. There is of course a force coming from the top, and that was 3000 newtons. Now that force of course divides over the left one and the right one. So that means each of these flexures will experience 1500 newtons of force. So we want to have, so F critical in our case is 1500, because we want to calculate basically what the reinforcement has to be able to withstand 3000 newtons, because it is divided over two flexures is 1500 newtons. There we go. So we know F critical, 4 pi we can find, E we know, I we do not quite know, because again it is that BH to the third, right, over 12. We don't know H, but we want to find out. And P is also an unknown, so we got two unknowns in this formula. Now, two unknowns, you might think, hey, we have two unknowns, we cannot basically figure this out. But I argue we can, because we can plug in different values for H. We know that it can't be any bigger than 0.7, but it can be smaller. So we are just going to increment 0.1, 2, 3, 4, 5, 6, and then see which value for P becomes a reasonable value. So, but first we have to rewrite this formula so that P is on the outside. So let's go and do that. Same trick, I divide this one by 1. So that means 4 pi squared times E times I over, times 1 is the critical force times L squared times 1 minus P squared. Alright, well, we want to know this one, so we're going to divide this term over the critical force times L squared, so we can take all of this away. Put this a little bit closer. Now, if we were to say what is then 1 minus P, wait, put it a bit more over here, 1 minus P must be then the square root of 4 pi squared EI, so that's BH to the third over 12, there we go, over the critical force times L squared. And now this is still 1 minus P, so how do we make this into P? Well, first I subtract 1, there we go, and then we do both terms times minus 1, so this becomes minus, and this becomes plus, and this one can go. So this is now our formula, basically, for P, as a function, sorry about that, as a function of H, or the thickness, in other words, because everything is known except the H. Now let's write down over here what the answers are for different values of H. So let's say we'll make a little table. So for values of h, what's the p-value? So let's write down, of course we know 0.7 is the absolute maximum. So write down 0.6, 0.5, 0.4, 0.3. So I'll just write that. I'll just put those in my calculator real quickly. So we have here the square root 4 pi, yes. So if I put 0.6 in my formula for h, then I get a p-value of 0.45. So that means approximately half of it is reinforced if we have a thickness of 0.6. Now, if it becomes thinner, 0.5, now the p-value is 0.86 or 87. So more of the beam basically has to be reinforced because my sheet is getting thinner, so the risk for buckling is getting higher without reinforcement. For 0.4 it is 0.93. Yeah, or actually 94. And then yeah, we can do 0.3, but you can imagine that it will come very close to 100% the smaller you go, so 0.97. So this is for buckling. Yeah. So we are now only looking at for what h values do we need what kind of reinforcement to prevent the thing from buckling. Now let's go on to the next phase, because another requirement was of course that 9 newtons and that the movement of 2 millimeters. Now we calculate over here that 0.71 was okay if we don't have any reinforcement whatsoever. However, now we're going to look at the formula with reinforcement, and it's this one. You can find it in the back of your book. So we have 12 EI over L to the third times 1 over 1 minus P to the third. Where of course the P is again that value for the reinforcement, and yeah, we've got in that I, we've got BH to the third again over 12. So let's rewrite this formula again so that P is outside of this thing. So first things first, K is already over here. So we are going to say K over 12 E I over L to the third. Yeah. So basically what I can do then is put L to the third on top. So it's L to the third times K. And that is now 1 over 1 minus P to the third. I do the cross thingy again, so that times that is that times that. So 12 EI is L to the third times K and times this term, so it's basically 1 minus P to the third, like this. We want to have the P to the third, so we divide this over L to the third times K, so I can take this away, and then also those brackets get lost. I'll take this term and put it over here. Now it's a bit different than in this situation. In this situation we had, we had 1 minus P squared, so both of them were squared. While in this situation it's 1 minus P to the third, so that 1 is not to the third. Yeah, so if that makes sense. So if we want to write away that 1, we do the same as we did before. We say minus 1, then this is gone, and then we multiply both factors by minus 1, so it becomes minus 12 EI plus 1, and this one also goes. So we're almost there. So the formula for P as a function of H is the squared root, the third square root of minus 12 EI over L to the third times K, where of course I is BH to the third over 12. So this is basically what we have, and then of course, almost forgot it, plus 1. So this is the formula for the value of P. Now let's do exactly the same what we did in the other one. So we are going to make a little graph like this, and we're going to say, okay, for different values of H, we have different values of P. So let's say again we have 0 0.6, 0 0.5, 0 0.4, well 0 0.3 I don't think is even necessary anymore. We already saw that it will become very high if we do that. So for the value of 0 0.6 we get a value of P 0.73. For 0.5 we get a value of approximately 0.87. Wait, sorry, I am doing it wrong. This is the buckling formula. My bad, my bad. Or is it though? Sorry, I'm a bit confused here. We say the third square root, let me just write it down again, of 12e, yeah, 12, 210 times, and then AB, then we have the 30 times h to the third, so let's say 0.6 to the third over, and sorry, in the meantime I'm putting this in a calculator, so my apologies, over 12, and then we have L to the third is 100 to the third times K, which is 2.25, we figured it out earlier, plus 1, there we go. So yeah, sorry, I was doing it correct. So indeed, so 0.6 comes to a value of 0.73. 0.5 gives us a value of 0.87. 0.4 gives me a value of P for 0.93. So, and does this make sense? Yeah, right. Because the p-value, the smaller we get, of course, the bigger that reinforcement has to be. Otherwise, yeah, that value will become very, very, very low. So, this is basically what we have figured out. Now we are going to try and see what kind of values make sense. So for 0.6, for instance, we have a value of 0.73. And for this one, it was 0.45. So the first one actually already makes sense, because for a height of 0.6, we need to at least have a p-value of 4.45 to reduce buckling. It can be more, of course, so it has to be bigger than this value, you can imagine. If it's bigger, the value, then we just increase that buckling force. Now the question was that the system has downward loads of 3000 Newton, so we need to make sure that it doesn't buckle under these loads. So, and it doesn't, see, so because that 0.6 value that we chose, we get a p-value for 0.73, and if we choose that 0.73, then we have enough stiffness in our system, and it will not buckle because the critical buckling reinforcement is 0.45. So 0.6 would do. Now let's see what 0.5 would do. In 0.5 we need to have a p-value of 0.87. My 0 is a bit weird. It is 0.87. And for the buckling force, hey, that's also 0.87. That's actually quite neat. So the 0.5 would also be okay as long as we have 0.87, the p-value for 0.87, that will also do, but it is very much on the edge. See, so it will be on the edge of buckling, and it's also on the edge of the force. So this one I wouldn't recommend. And for 0.4, we just saw, it's wrong because 0.4 doesn't work, because then we need a p-value of 0.93, and over here we have a 0.94 actually in this value. So yeah, that's also on the edge. I wouldn't recommend that. So basically what we have determined in this small exercise is that if we have, for instance, a height of 0.6 and a p-value of 0.73, our system will be able to move and it will not buckle under these loads, because that is what we have figured out over here. So that was how this exercise is done. It's quite a tricky one. There's a lot of thinking involved and a lot of theory, but hopefully this helped you a little bit in figuring out these kind of exercises. Alright, that's it for today.